Welcome to part 2 of our lesson on section 3.3, differentiation formulas. In this lesson, you'll learn about finding the derivative of a product or quotient of functions. Let's go back to one of the functions we differentiated in part 1 of this lesson. This is function h from example 3. You might remember that we multiplied these binomials together first and then found the derivative of each term. Is there a way to find this derivative without doing the multiplication first? Our first instinct might be to just find the derivative of each binomial and then multiply those together. Does that work? Well, the derivative of 3x plus 1 is 3, and the derivative of x squared minus 5 is 2x. Multiplying those together definitely doesn't give us 9x squared plus 2x minus 15, so that didn't work. That means the derivative of the product of two functions is not the same as the product of the derivatives. Instead, it looks like this. Suppose we have a product of two functions u and v. The derivative of that product is equal to the first function times the derivative of the other, plus the second function times the derivative of the first. To make this easier to remember, let's take a look at the proof. Suppose we have a function called capital F, which is the product of two functions, little f and g. Then the derivative of capital F looks like this. To make sure that things come out the way we want them to, we add and subtract a special term, in this case f of x plus h times g of x, without changing the value of the limit. Then we can factor an f of x plus h out of the first two terms, and factor a g of x from the last two terms. Break those into the sum of two limits, and then break each of those into a product of limits. If we substitute 0 for h in the first limit, we get f of x. The second limit describes the derivative of g. The third limit is g of x, and the fourth limit is the derivative of f. Translating into the notation we used on the previous page, think of u as f of x and v as g of x. Going back to that example from the previous lesson, let's now use the product rule to find this derivative. First, choose one part of the product as u and the other as v. Does it matter which is which? If you said no, it doesn't matter which is u and which is v, you're correct. The order doesn't matter here because our rule involves multiplying and adding, which are both commutative operations. Find the derivative of each of these functions. I like to write the parts in this formation because now I can imagine crisscrossing from the top left and then from the top right to form the derivative. Distribute and add like terms, and this matches our answer from yesterday. Now at this point, you might be thinking that it took us way longer to find the derivative using the product rule today than it took us yesterday when we just multiplied first. You'd be right. We won't normally use the product rule in cases where you can simplify the product first. In later lessons, we'll add other types of functions to our list, such as logs, exponential, and trig functions. When this happens, the product rule will feel more useful. Part of your job will be to recognize whether it's appropriate, helpful, or even necessary to use the product rule. We also have a rule for finding the derivative of a quotient of functions. We won't look at the proof for this one, but it's very similar to the proof of the product rule. Suppose we want to find the derivative of the quotient of two functions u divided by v. The quotient rule says that the derivative is equal to v times the derivative of u minus u times the derivative of v divided by v squared. As an example, let's find the derivative of x to the fourth minus 4x plus 3 over the square root of x plus 1. As with the product rule, I would suggest writing down which function is u and which is v. When using the quotient rule, u must be the function in the numerator and v the function in the denominator. Then find the derivatives. To use the quotient rule, I imagine crisscrossing first from the top right and then from the top left. That works for me because I like to work visually. If that doesn't work for you, then you'll need to come up with your own way of placing the terms in the correct order around the subtraction sign. Here's the derivative. Now I want you to notice two things here. The first thing you should notice is that, unlike the product rule, the quotient rule is immediately useful. It would not have been easier in this problem to divide first before calculating the derivative. The second thing you should notice is that you're starting to see some problems in which you can appreciate not having to simplify your answers. Now that you know the quotient rule, don't go trying to use it every time you see a quotient. If you do, you'll be wasting a lot of time. Here are some examples. In function f, the denominator is a monomial. We can easily divide x into each term, and then just use the power rule to find the derivative of each term. By the same reasoning, we can rewrite function g as the difference of separate fractions, and then just find the derivatives term by term. In function h, we can use a negative exponent to rewrite the denominator, and again, avoid using the quotient rule. As a good rule of thumb, if you start to use the product or quotient rule and find that u or v is constant, then you shouldn't be breaking the problem into u's and v's in the first place. Do you know why? Here's a hint. What happens when you take the derivative of a constant? Here's an example of how a product rule question might look on the AP exam. We have differentiable functions f and g, and some information about them is given in the table. H is negative 4 times the product of f and g, and we need to find h prime at 1. We're being asked to find the derivative of a product, so we need to use the product rule. If we take u to be negative 4f of x and v to be g of x, then the product rule says the derivative looks like this. Substitute from the table, and our answer is negative 36. This concludes part 2 of the lesson on section 3.3, differentiation formulas.